Welcome to another week of Marshall Land. We're going to do the green screen this week.
Are we recording?
Yes, we are.
Okay.
And reason for that is there's so much fine detail going to be happening up in front of the room. I want to make sure that the camera captures the best images possible and that you can clearly see some of the equipment we're working with here. Okay, so we got some announcements, so we're going to cover a little bit of that first. That is not a popcorn machine you're listening to. That is a Geiger counter, and so we've got some background radiation that we're listening to right now. I just thought you should know. So the first thing that I want to cover is Northwest Nuclear. We look very carefully at what happens week over week, and we do our best to try to learn from those experiences and compare them with previous weeks, months, years, and find the sweet spot that best suits not only the program but your scientific interests. That said, this last year we tried to do something called the wagon wheel. We were in the middle of COVID. We had to deploy an air system. There were a lot of things that happened suddenly that forced us into a situation that was less than optimal. So this hasn't been a year that went as according to plan, or that is going to go down in the books as one of my best, that's for sure. We did manage to come online in September, which we said we would do. We had a moment where we blinked for a couple of weeks and then managed to pick back up again when we got a more formalized process around our respirators, these marshmallow suits. Turned out that was a very stringently regulated, state-regulated program and required significant preparation. So we had to kind of back up a step in mid-step and then move forward. So, okay, we've learned that. We're going to essentially follow the lead of the public school system, and we're going to shut down on the 11th of June. Let me tell you what this means. We're not necessarily taking a summer break. What we're doing is we're changing formats. After considerable analysis and looking at what worked and what didn't work, and some of the stuff we did on the wagon wheel was to try to get you some exposure to as many different types of technology and infrastructure in the scientific world as we could, so that you had a broad experience of different things. But what we now see is that really didn't allow us to do a deep drill down on any one thing. We spent a couple of weeks on this, or a week on that, and we did a few of these, but we never really got deep into anything. And after looking at that, that's really not what we designed the labs for. We wanted to be able to do some deep research. We wanted you to experience what it's like to do some deep research. So we're going to change the way that we go about this, and we're going to implement something called the journey. the journey. Let me tell you what a journey is. A journey is an experience where a mentor, like me, or like you, decides that they want to pursue some particular scientific investigation or process or exploratory research, and so they write it up, and we review it, come up with a budget for it, and then we publish an invitation on our website. The invitation goes out to all the qualified members. There are those that will be qualified for on-prem and those who will be only qualified for Teams or off-prem participation. On-prem requires a little more. So we want you to have been through the safety and radiation training and all that. If you have a red badge, you are open to be a team lead. You are open to be a mentor and actually author your own journey. So it doesn't have to just be an adult. It can be anybody with a red badge. Now that's pretty cool, because that means you can figure out what you want to do, and you can basically put the paperwork together, call your team up and say, hey, we're going on a journey, and get a bunch of folks and pile in, and then we send an invitation. You might wind up with a few other stragglers, and then the rest are going to get pushed out online, and then you lead it for a certain number of weeks or months, depending upon the scope and the type of research you're doing. There will be some 2-week, 3-week journeys. There will be some 2-month, 3-month journeys. Some of the journeys will be biomedical. Some of the journeys will be a journey in radiation safety or in nuclear fusion. Might have a journey in welding. Might have a journey in shop. Might have a journey in television production. Might have a journey, who knows? We have the facilities. What is going to determine largely what we do is what the level of experience is of the mentor that's leading. Now, an example of this is that I received a call from a gentleman who's a good friend of mine, who's also the director of Boeing Radiation Effects Lab. And somebody who is a close friend of his is retiring, and that individual is going to get bored about the middle of summer. That's a planned event. And he's going to want to come play. And turns out that while he was at Boeing, he fabricated some very advanced gamma camera research technology. And that technology still exists. It's in storage down at Boeing. And Boeing is okay with him using that equipment to lead a journey. Some of that journey might happen here. Some of that journey may happen at Boeing. Fun project. There will be a student lead who works with him to help him find the ropes and the handholds and the things that work there. I have already approached one of our students and let that person know that if they are still available when the journey happens, they've got first call on it. there are some other highly gifted, highly technical people I work with at Microsoft who are capable of leading some journeys into some amazing technology and have expressed a desire to do so. I haven't had a format that would allow them to step in and do that until now. That's what this allows, is that I can reach out to companies and friends and colleagues and contacts, and we can have visiting engineers and scientists and astronauts and who knows what come in here and share their experience and take us someplace special, someplace only they can. And our job is going to be to provide the facilities and the technologies to facilitate that journey. And you, the students, get a chance to come along and learn from inside the experience what it's like to do science at that level. Some of that science will have never been done before. It will be cutting edge research. It will be stuff that is not just academic rhetoric. It's actual, you're out on the edge, you're doing something new, no one's ever been there before, and you're going to get a chance to publish something. And that's a significant opportunity. One of those really neat things. Now, some of you, depending upon how COVID works and how the vaccine works and how the variants work and how the boosters work and all the rest of it, if you find yourself coming back for a spring break and want to jump in for a couple of weeks, or you're marooned because your college is temporarily locked up, remember us, we're still here. Okay, so those things said, again, June 11 will be our last formal day of this school year. And we're going to stand down for a couple weeks while we refabricate the website to facilitate these journeys. And we'll also be talking to some people behind the scenes who've indicated an interest in leading a journey and find out which journeys are going to be up first. And then within a couple of weeks, you'll start seeing postings on the site and you'll start receiving mail, call it spam. And yeah, and you'll be receiving these invitations, and it'll be up to you to decide whether that's a journey you want to go on. Now, one of the positive things that we get out of this is that because you made a decision that you wanted to go on that journey, there's an assumption. And the assumption is that you wanted to go on that journey. Yeah, I know but sometimes you have to spell these things out. The reason is because we don't want people who are just getting dragged along in the academic conveyor belt and all of a sudden they're involved in a topic they have no interest in whatsoever. This solves that problem. If it's not something you want to do, don't go. Pretty simple, huh? If you're into nuclear physics and, oh yeah, biomedical makes you throw up, you don't have to go on the biomedical. Go on the physics journeys. We'll see after we've run a few of these, and the idea is that when we'll cover them on a week-to-week basis as best we can with the studio and the cameras, publish the information up so everybody can kind of follow along behind. And we'll take a look at what we're accruing as far as documentation and video and how best to present that so that people can get their head around what's going on and how it might fit in different media formats. I'm kind of excited about that part. Could wind up on Channel 9. Okay, so that's the journey plan. Thank you for your patience. All of this has always been an experiment. We're here not because there aren't enough schools. There's enough schools. But what we don't want to do is do what's already been done, because we already know how that works. The whole principle behind this is, hey, we've got a blank check to do it our way. I did it my way. Yeah, okay, well, that's kind of the story. We get a chance to explore some ideas and listen to some feedback and learn some things that we otherwise would never get a chance to learn by trying some things that have never been tried. So this is an experiment in college prep, and that's what it's designed to do, designed to be, industry prep. And so we actually started a journey last week. Didn't tell you then that it was a journey, but it was. And I kind of had a mind to start down that road. Now, during last week, we covered fundamentals of radiation. We talked about alpha, beta, and gamma, and we talked about different kinds of radioactive isotopes and different kinds of detectors, and kind of what to expect when you're measuring various kinds of radiation, the basics. Now we're going to kind of head into the journey, and I'm going to talk a little bit about what the journey hopes to accomplish. Last week we started talking about the various detectors. There's ion chambers, and there's scintillation counters, and there's cloud chambers. There's a number of different kinds of radiation detection. Probably the most commonly used and the most valuable in terms of information gathered is the scintillation counter. And there are a variety of scintillation machinery, liquid scintillators and solid crystal scintillators, plastic scintillators, and they all basically have certain things in common. This is a photomultiplier tube, and it's a rather interesting looking little gadget. It's a tube with 14 pins on one side. When you take the cap off, you can look down inside, and there's a little port in the center of it that collects light, and that couples to a crystal or a piece of plastic, and energy from radiation comes up into that plastic, and we have a process called scintillation where those particles result in the release of a photon. There's a momentary flash of light within the crystal. Well, that flash of light then comes up inside this photomultiplier tube. And the reason it's called a photomultiplier tube is it takes a photon and it multiplies the effect through some cascading of charged plates in here. And it results in a pulse that is then amplified and sounds like popcorn. And that's what we're listening to over here on the side. You can probably hear it. And so it is a light-driven technology. Now there are scintillation liquids, there are scintillation plastics, and there are scintillation crystals commonly in use. and they come in various sizes. Now, this is a sodium iodide scintillation. This is a 5-inch. This is typically used in mining. It's a big boy. I'll go ahead and fire it up here. When we change scintillators, we have to unplug the USB cable first, and then we can move our high voltage probe over to another scintillator. If we don't unplug the USB cable first, not only do we risk electrocution when we unplug this thing, but we also will blow up the amplifier in the electronics. So each and every time we have to unplug and plug in when we change scintillators. And then it takes a moment for the system to recognize it, and then you hear the noise pick up again. Now in this particular case, we're not going to hear a lot of noise because it turns out that this one has had a hard life. He's kind of been abused. However, he still has some life in him. And what we're going to do is we're going to take an isotope. I've got my handy dandy sticky stick here. This is an invention that a student came up with that allows us to use sealed sources safely. And you can hear the kind of waterfall sound when I hold this up against the side of this scintillator. And that's showing you that there's an input. We're going to go one step further. This is a visual representation, and I'm going to turn on our visual representation here, and you can actually watch as we form some data using this scintillation crystal. Now you'll see that all the scintillation data is occurring down at the low end of the spectrum, and it's all spread out and it's all kind of a wash. Well, there's a reason for that. And the reason for that is because this particular scintillation crystal, like I said, has had a hard life. Somebody dropped it, and it's broken internally in more than one place. And the problem is that, especially with sodium iodide crystals, if there's a crack in the crystal, it is no longer capable of being used for accurate radiation measurement. You can use it as a Geiger counter to detect the presence of radiation, and you might even do fairly well at measuring relative quantity of radiation, but you cannot measure energy. That's something that's reserved for a healthy crystal. This one is no longer healthy. So, in response to that, I wanted the good 5-inch scintillator, and this didn't turn out to be a good 5-inch scintillator. And I want to tell you, this thing is heavy. Let me just hand it out here, pass it around, so you can all kind of heft that. And so I got upset, and I went out and I bought another 5-inch PMT. That's one of these that's 5 inches in diameter. And because I wanted something that would detect radiation, gamma, and neutrons, I went with a plastic. And that plastic is called BC412. So here's the BC412 scintillator. As you can see, it's substantially lighter. Okay. And we're going to fire this puppy up. I whipped him up in the garage this week. Okay. So there we can see the input on it. As you can see, it's all crouched down there. Now I'm going to take a little bit of gamma. As you can see, out there in the middle of the spectrum, we've got a mountain building. Now, for reasons that aren't clear to me, our audio seems to have gone away. I'm going to see if I can identify what happened. Oh, there we go. No particular reason. And we see this gamma, and we see that it has a definite peak. Well, that peak is not well defined, and hence plastic, although it's a very effective radiation detector, doesn't do a real good job in giving us a sharp peak, which we need if we're going to do isotope identification. You see, the purpose of this is we want to be able to identify a particular isotope, and it may be just a narrow distance in terms of energy output from another isotope, and so we need as much definition as possible. We need nice, sharp peaks, and this won't do it. So again, we have something here that can see radiation, actually see it quite well, but it's short on its ability to differentiate. Now, I'm going to switch back to our original sodium iodide crystal here. Excuse me while I cut my finger off. There. See, now I can use my cell phone. Now, I've just cut over to the reactor room, because what I'm going to do while you folks watch is I'm going to take our new scintillation, I'm going to go in and I'm going to expose it to some neutrons. Reactor's all warmed up, so I invite you to watch. Hello. Now what we're going to do here is I have this set up on a meter. Let's see if I can finagle some stuff around here, make a table available. Now I'm going to come back and adjust the camera because I want you to be able to see that dial. I'm working with a robotic camera and I can only adjust it from master control. So I have to come back to the control room. We'll go right down on that puppy so you can kind of see him. I want to kind of put the meter in the corner of the screen. Okay, that should do it. Okay, I am turning on the high voltage, turning on the gas, lighting the fire, and we've got neutrons. We've got a lot of neutrons. And we're going to have to click this down a notch. And you can see the dial goes way down when the neutrons go down. When the neutrons go up, the dial goes up. And what I'm going to do is I'm going to take our probe and I'm just going to hold it up to the reactor. As you can see, it definitely responds to the neutrons that are coming out of the reactor. Now that's very handy because now all of a sudden we have a single probe that can detect alpha, beta, gamma, X-ray, and neutron. Whereas in time past, we have had to have one probe for ostensibly X-ray, one probe for neutrons, and one probe for gamma. Okay, so we're back here, and we can see that this little lightweight, essentially tinfoil probe, we've just taken some silicone tape and taped the PMT crystal onto the photomultiplier tube, and then wrapped the whole thing in aluminum foil and kept wrapping until the count died down, because the photomultiplier tube will respond to ambient room light just as quickly as it'll respond to light in the scintillation crystal. And so you don't want any light leakage coming into the crystal other than the radiation that you're trying to detect. So, hey, that was pretty good. We got ourselves a crystal, and frankly, this was cheap. That bigger scintillation heavy-duty one, those run about $12,000 to $14,000. I built this one for about $300-400. So I'm very pleased with this. I am probably going to donate it to a certain college where I'm a mentor of fusion research, Puget Sound University in Tacoma, because they have a program and they're looking for a good detector for X-ray. And this will work wonderfully for X-ray. It'll also work for their neutrons, which they don't know they're going to need yet. Well, actually, they know it, but they haven't got any neutrons to count. So at this point, it'll be a while before they do. However, they are going to have X-rays relatively quickly, and we definitely want them to be able to measure that. Okay, so I said, you know, hey, this is a journey. Well, a journey is an investigation or a research or a pursuit that takes the organization to some specific new destination. And the destination that we want to go to on this journey is we want to develop a sophisticated and accurate scintillation-based isotope identification technology. We want it sensitive enough to detect radiation in food, milk, plants, and we want it definitive and discerning enough so that we can identify specifically what kinds of radioactivity are in those materials. Well, to do that, as we have been learning, we have to have a very accurate crystal. That's really at the bottom of this. So the journey starts with having a good crystal, and the crystal in here turns out is also whacked. It doesn't scintillate the way it should. The one in the larger one doesn't scintillate the way it should. So I reached out to a good friend of mine named Steve Sesselman, who owns a company called Gamma Spectacular in Australia. And down under, yeah. And so he and I chatted, and it turns out that he has in the back of his storeroom a 3-inch by 3-inch sodium iodide PMT crystal in pristine condition, encapsulated with a viewport ready to attach to a 3-inch PMT. $1,000. And I got to tell you, that's cheap. They usually are a lot more. So it's coming by FedEx. It'll be here hopefully this next week. And we're going to build it a home. Because there's a couple of things that we want to be able to do. First of all, we want to be able to connect it to this PMT. So that means we need some kind of a envelope to put it in. And I'm opting to do essentially the same thing I've done here. Use a piece of PVC pipe and a reducer flange, which neatly tightens up around the connector. And we'll use a different bottom, a thinner material to get a little better sensitivity. But this makes a really robust container. And you really have to whack one of these things pretty hard in order to bust it. Nevertheless, they do bust. You drop it on the floor, it's history. So that's the direction we want to go. We're going to leave this one alone. We're just going to buy some new parts. I can afford the sewer pipe. And build ourselves a new one. And the journey is going to be to build the probe, to build a suitable oven to house the probe. You say, oh, oven, what's he talking about? Well, if you remember last week, we had some lead bricks out here on the table. And so we're going to go visit those lead bricks. Come on. And you can see some lead bricks there on the table. Now I'm going to go visit those lead bricks. So continue watching. Okay. Hello. So I'm down here with the lead bricks. And the reason I'm down here on the floor is because lead's one of those things you don't want to fall off a table. And the closer to the floor you're working with it, the better. So what we've got here is a brand new skateboard. Well, I wouldn't exactly call it a skateboard. It is a dolly, and it's a very, very heavy duty dolly. And I'm going to take this lead bottom off of here and show you this puppy. Pretty cool. These are very, very robust casters. They're rated at several hundred pounds apiece, and the total carrying capacity of this dolly, which is made up of aluminum rebar and bolted together, is over 1,000 pounds. And we need something that strong to hold the kind of weight that we're talking about holding. So we're going to take this lead bottom, and this lead bottom has a hole in it. And that hole allows us to insert a isotope from underneath up into the cavity. I don't think you can see my finger, it's wiggling there, but that hole goes all the way out. So if we had our PMT sitting in here, we could insert from the bottom and present a sample of something to our PMT inside this lead shield without having to open the lead shield. The next thing that we're going to do is we're going to take these lead bricks and we're going to configure a chamber. And I'm designing this lead chamber such that there will be a cavity in the middle and that cavity in the middle is going to be just the right size to hold a 3-inch PMT. And then finally, now that we've got our lead bricks, we have a lid. Now this lid has a place for the electrode to connect to the PMT in the cavity. So we can take this lead lid, put it on our cavity, and theoretically that would seal our 3-inch PMT down inside, and we have a place for the cable to actually come out and connect. And lastly, as you can see, we have a hole on top. We'll place a lead brick over that hole. And this is ostensibly the design of our oven. And this thing moves relatively easily on this concrete floor, so I can roll it from laboratory to laboratory. But it's very, very heavy. If it falls over or falls down, it's not going to do that much damage. It's not going to break my floor. But we're going to tape it up with some very strong glass tape so it won't fall apart easily. So we've got our radiation oven for our 3-inch CMT that's on its way, already put together, figured out, and it'll provide enough silence or isolation from the background noise of radiation around us to prevent it from being overrun with just ordinary cosmic radiation coming in from the sun. Okay. What are we doing here? One moment while we switch back to reality. Okay, we're back in Marshmallow Country again. Now, so we have our 3-inch PMT. We have our crystal on the way. We have a tentative design in play for our housing for our new scintillator. We've now defined the oven that it's going to reside in. The next thing that we need is a way to couple it up to the computer. Well, that's already been provided. This is a Gamma Spectacular, again from Australia. Real handy little gadget. Let me see if I can get a better view of it for you. So it looks like kind of like that. And that one, as you can see, is showing 1200 volts right now. Okay. So we've got the device that converts the high voltage signal that's coming from the PMT into a USB signal that we can send to our computer for analysis. That's kind of fun. Think we're headed in the right direction? Okay, well, we're not done. The next thing that we need in order to really be able to do some fine-grained analysis is we need sufficient computing horsepower. And the computing horsepower that we've been working with over here is an 8 gigabyte 2.66 gigahertz Pentium. It's a dual core. For those of you who aren't savvy with computers, that's like saying, I got an Edsel. Now, for those of you who don't know what an Edsel is a really old car. And it wasn't popular when it was in vogue. In fact, Ford got laughed at because they said the grill looked like a horse collar. Consequently, if you had an Edsel, you had a dud. A real lemon. This is not the computer that it needs to be. So we need to fix that. And so I decided that it was necessary to upgrade our computer. So I got a 500 watt power supply. You know, an Edsel might be valuable someday. So I have another rack mount server here that we're going to be using tonight to mount our 500 watt power supply in. But that's not enough. We had some specific problems. So I got this little guy. I don't know if you can see the box clearly, but this is an Intel i9 Series 11. That is the top end chip currently on the market. This is 8 core, 8 dual cores, so 16 threads. Lots and lots of horsepower, 3.6 gigahertz, I think. Let's see, I think it says on it. No, it doesn't. 9th generation. Nice. Anyway, so to keep that cool, we're going to add an Intel cooling solution. So this is a thermal solution made by Intel. We'll be installing that. And, oh yeah, we need some memory. So here's 2 sticks of 3200 16 gigabytes a stick for a total of 32 gigabytes of, 3400 latest DDR RAM. And then this thing has a hard drive in it, so we need something to store our data on. So I got another hard drive, only this is a little guy. There's a reason he's little. Comes with this handy little booklet. And he's only that big. About the size of a pack of cigarettes. And he's really thin. Yeah, like that thin. Woohoo! That's thin. He's 500 gigabytes of solid state SSD, which is, again, state of the art, super high tech. So we're building a rocket. This is a gaming machine. This is something that the guy who's playing Halo is going to be drooling over. And oh yeah, we need a motherboard to mount it on. So I got a new Prime Asus. This is a Z390A top of the line gaming motherboard. And we're going to stick all that stuff inside this cabinet and connect it up. And if time permits, we'll actually get it to post. And what you're going to get to see on this particular part of the journey is you're going to get a chance to see what it takes to build a computer from the ground up. Because doing it this way is a whole heck of a lot less money than going out and buying one off the shelf. I promise you. Doing it this way, though, comes with a few surprises. You'll see what I mean as we move along. Especially because we're retrofitting it into a 1970s vintage U4 chassis. So that'll be our challenge. So I'm going to shut this computer down and make room on our table, and we'll open it up. And I'm going to need a volunteer tonight to play cameraman. Any takers? Oh, I get to pick someone?
I'll try it.
Okay. Caleb, come on up.
Great.
Okay. Now, what I'm going to ask you to do, we're going to unbuckle you for a moment. Is this little guy unlocks, so you can kind of swivel him around and tilt him. And you may have to, oh, we got one locked. Okay, so there we go. We got some movement this way and some movement that way. Kind of want to hold the tripod with one hand and hold the thing with the other. That's your targeting camera.
Okay.
So what it sees, everybody else sees. I'm going to switch over to your camera, and you're going to focus on me when I'm talking.
All right.
And focus on the gear when we're nutting and bolting.
Should I mess with zoom at all, or just leave it at?
Yeah, do you know where your zoom is?
Nope.
Okay, let's, because you're going to need the zoom.
Okay.
So this is your zoom, forward, backwards.
Okay. All right.
Play a little bit.
By the way, how's our other camera person doing?
Yeah, that is a point. Lynn did take a tumble. She is a lot of pretty colors. There was considerable bruising. She didn't break anything, but she's down for a while, running on a reduced schedule until all the pieces and the super glue works and she gets back together again. Our faithful dog Coco is taking good care of her in my absence. Yeah, it's been one of those. Okay, let's see if I can find the right camera for this. I think that's the one. little trouble here, an argument, I would call it. Ha! There we go. Okay. So, we're going to go to work here. We'll start by closing this guy out. And shutting him down. We'll take this guy and set him out of the way so we can bring him back to an Edsel dealership at some later point in time. Now these are what are called U4 chassis. They're rack mount. I've hung on to them through the years because computer technology's evolved a great deal. And the nature of computer technology doesn't always fit the same footprint that it did. And while it's usually smaller, sometimes there are surprises. Now, there are some structures in here which are provided to allow you to attach things. So like this aluminum plate, you can actually bolt hard drives to it and have a whole range of them. And I have two such aluminum plates inside. And that reveals our chassis. And in here you can see the existing motherboard and the power supply, which is back here in the back, and some additional hard drive structures, but they are for hard drives that are so old that the cables and the technology that supported them are long gone. And so we're talking highly antiquated. I'm just going to throw that away. The power supply that is in here, we might have enough to use it, but I think it's like, we'll have to evaluate whether or not this particular power supply has enough connectors to run that new motherboard. It does appear to be an updated supply. It's not entirely without merit. It's certainly much newer than the motherboard that was in there. And I'm just ripping cables out of here. Things that we will not need in the go forward. There are some connectors for some fans that'll be handy. And most importantly, there are some wires here that are used to connect to the pins on the motherboard to turn it on and off. So now we're down to the motherboard, and it's a CPU combination. We'll remove the video card. And this is a really, oh, that's not even a video card. That is a network interface card. The motherboard itself should have a, no, motherboard was so old that it doesn't even have a network interface connector, which is why this board was in there. So that was necessary. It also had support for an older technology. The cables aren't even available anymore. So again, don't need that. And now there are simply a range of screws that are holding this motherboard down. If you're going to do this work very much, one of the things you want to do is you want to take your Phillips head screwdriver and hold it up to a powerful magnet, so that when you unscrew a screw, it hangs on to it. It doesn't fall down inside the machine under something, and then you're dancing around the room, shaking the machine like some kind of a lunatic, trying to get the screw out from underneath wherever it fell. Those are not good moments. Okay, we only got a couple more here to go, and then the motherboard itself is going to be able to take out, and we're going to be ready to put our new one in. So here is the old motherboard, and that is definitely an Intel Pentium chip, and I can look at these connectors. This particular one is a reset button, and then we've got another one here. This is the LED lamp. So you got a power LED. We've got the LED for the hard drive. We've got a reset switch. And we've got a power switch. And those are all nicely labeled on the sides of the little black phenolic connectors. And we'll be using those, so we definitely want to keep track of them. Okay, so we got the motherboard out. That'll make a nice doorstop. And we've got in the bottom of this, let's see if I can pull up one of these and show it to you. This is a little brass guy. And it's called a standoff. And it's only about a ½ inch long. And the motherboard actually rests on these standoffs, and screws go down through the standoffs and connect, hold the motherboard onto the standoffs, and the standoffs screw into the base plate of the chassis. So that's how that connects. Got a few other things here. Probably be good to get them out of there, but I'm not sure how much work I want to go to. Alright, so I've got all the cables up here in a fist. And the next thing I'm going to do is I'm going to turn this puppy over and give it a good shake. And there's the reason. Parts. You don't want metal things rattling around inside this thing, because it's going to come back to haunt you. This is a drive enclosure, I think from the early Jurassic period. Yeah, maybe Palean, no, it's Jurassic. Okay. So certainly not part of the reality that we're headed towards. All things considered, we're gonna cut over, and we're gonna replace the power supply too. And the reason for that is because A, we've got one, and B, I don't want to find out after I put it all back together again that I need to rip it all apart and replace this anyway. So the amount of time that it would save me isn't worth it. So there's the power supply. It's a nice one. I'm going to hang on to it in the event that I need a power supply, because one goes kapow, because it is a later vintage machine. Okay, so we'll start with that motherboard. This is a relatively high-end motherboard. Asus makes good stuff. And they come in this kind of smoke-colored bag for a reason. These are anti-static bags. And in this particular case, this anti-static bag is housing a piece of technology. This really is a very special motherboard with a lot of very high-end surface mount, high-density electronics. It's probably 6 or 7 layers thick of technology. I'm just going to gently set that on the deck in there. And underneath the cardboard, down in the bottom, there's a grill. And I don't know if you can point the camera down inside here, but there's a cutout in this guy that's made for a grill. Smart people. They came up with this. So here's this little grill, and it's mated so that when you mount the motherboard, it neatly matches all the connectors so they all stick out the way they should. Hey, that's pretty cool. So if I just turn that around now in the direction it's supposed to go, it just sticks, pops right in that hole, ready to go. So I turn my motherboard around and I can lay the motherboard in there and screw it in, and it'll match up perfectly. But the first thing I have to do is I look at the motherboard. Want to zoom out? I look at the motherboard, and there are, again, these holes that are supposed to mate for the standoff. These standoffs that are in here. And the holes in the motherboard I'm putting in don't necessarily occur in the same locations as the motherboard I took out. And I need to check one by one and make very sure that the holes and the standoffs line up properly, because if I don't, I can wind up with a standoff that's actually touching the bottom of the motherboard at an unknown location and shorting out pins, and I power it on and it blows up the motherboard. It's gone. And you're $300, $400, $500 down, just that quick. So this is a real serious moment. This has to match the standoffs absolutely. So I'm going to go through here and I'm going to look at the board and the light, and I'm going to say, okay, I've got one hole here, and one hole here. That means on the front, I can see 3 of these standoffs need to be there. And I look down inside the machine, and guess what? There's 4. Right there, I would have blown up the machine. So, we're going to stop. We're going to find out which one of these is the rogue in terms of position. And then that one has to come out. So there's one standoff that shouldn't be in there. Now I go up a little further and I say, okay, there's a standoff there, and a standoff there, and a standoff there. So there's 3 in the back. Do they line up? And they do. But it doesn't stop there. Turns out that the standoffs go back another row. This is a bigger board than the one that was in there. And so I'm going to take the one that I took out and I'm going to fill one of those holes, but I need 2 more to fill out the pattern.
Carl, I've seen some people wear anti-static straps when they're working on a computer. Is that not needed anymore, or is that old technology?
No, it is it is needed if you are not wearing rubber gloves
Okay.
and insulated on a carpet, etc., etc. I have an advantage here, and under certain conditions I would. So now I'm going to need to go get a couple of standoffs, which I have in a drawer, and I will return momentarily. One of the things about being a computer engineer is you learn to be a pack rat, because sooner or later you're going to find yourself in exactly this situation, and you're going to need to reach down inside your bag of tricks and come up with a couple of standoffs. And I've been a computer engineer for more than a little while. Therefore, I'm a pretty good pack rat. And so now, if you take a look here, I got a box. And inside this box, I have the mother load assortment of standoffs for just occasions like this. So we'll pull our motherboard back out here. And we'll take one standoff as a sample, and we'll go looking. I think what are these, metric? Okay. Well, in that whole box, there are no mates that will work for me. So I'm going to take my one good standoff, I'm going to put him out in the middle on the back end, and I'm going to make note as I'm assembling here that I'm going to have to come back at a later point in time and add those two standoffs. But this will get me going again. And right now, that's what we need. Okay. So I'm wandering around in here in my mind and my eyeballs, making real sure that all the little holes have a standoff underneath them, except two, which we knew about. And now we're ready to go ahead and put those screws in. And we're not gonna tighten them down real hard. That's a mistake. We're just gonna get enough of a bite here to get them started. Because once we got it all in there, we're going to have to do some alignment. There's screws with different size threads here, and you have to pick each one up and make sure you don't wind up putting the wrong thread that'll come back to haunt you later too. Okay. So now we got the motherboard in there. There's a clip lock assembly spring that opens up, and it has a plastic dummy holder. It's a cover for where the CPU goes. So the CPU goes into this and then locks down. And the CPU is our most fragile, most expensive, most terrifying part. We're going to go ahead and mount him next. Like I said, he's an i9, top of the line. They got all this propaganda that comes with him. A little trick finger lock on the cardboard here. to allow you to get in and get your chip. Now I want to take a moment and just try to show you this. It's really quite pretty. We'll wait, don't come in too far because it won't be able to focus. We're going to wait for it, see if we can catch the focus. Come out a little further. A little further. Just let me check and see if the autofocus is on. Autofocus. Let's try focus assist. Yeah, it's not grabbing it. Let's try this. Yeah, there we are. That's working. So, pretty gold. You can just see an enormous number of contacts. The amount of connectivity going in and out of this package is just amazing. But every single one of those little dots is a connector. And so the alignment of this thing is huge. It has to be very precise. And if you'll notice, as you look at it, the corners are different. You've got one corner with one missing pin, you got a couple corners with 3 missing pins, you got one corner with maybe 4 or 5 missing pins, and that gives you orientation as to how it sits down on the motherboard. Because you look down on the motherboard and you're going to see the same pattern. Okay.
Just to let you know, Carl, it's 15 till.
Okay. We'll get the CPU in and we'll get it locked down. Okay, the CPU is in and it's locked down. And very quickly, the next step in that parade, I don't have time to put in the motherboard, but I will show you this piece. I hope this is interesting to you because someday you may, if you don't build a computer from scratch like we're doing here, you'll have an occasion to repair one, and or at least do some diagnostic work. And if you're terrified to even take the cover off, that's not a good thing. So here are the memory sticks. And they're set up in what I call a pop and drop packaging. And so when you pop it open, it flies up in the air and you're dropping your memory sticks all over the place. So you got to be really careful. You break the edge on these and they're toast. These are, again, high-end memory. they only go in one way. And so we're going to insert them into the motherboard. And there's a slot and then it locks. So we've got one in. And you can hear them kind of pop in and pop down. And they lock down, so we got the memory in. I'll show you one more trick. What time we got? How long?
About 10 minutes.
About 10 minutes. Okay. Okay, so this is a cooling solution. And there's our cooling solution. And it's a fan, and there was a protective plastic cover over the bottom of this because there is a sticky material that you can just see here. It's outlined. This is the material that bonds the CPU to this copper cooling heatsink. So there's a fan wire here and a great big heatsink, and this is a cable that's safely mounted to the side of this to keep it out of the way while it's in transit. But we'll plug this into the motherboard, and then this essentially just pushes down onto the motherboard. There's 4 holes, and there are 4 locks that you lock with a screwdriver. So this appears in a perfect square, and as such, there really is no right way or wrong way to put it in. And then we take our screwdriver and they turn about a quarter turn to lock down. And this one is now locked down. We got our little fan cable. We can put them on our little fan connector. Got a couple of different places we can go. Okay, so we got our fan connector. And we can use a little guide to keep the wires out of the way of the fan blade. And we've got our fan in. And at this point, our system is assembled about as far as we can go tonight. I'm going to go finish the power supply, and the video card didn't arrive today. Supposed to, but it didn't. So it'll show up during this next week. I will finish putting that in, and then we can load the operating system. But this is the finished product. So you go ahead and zoom in, take a look at that. And you can see we've got our fan, our memories down here, the CPU's underneath. We've got our motherboard set up so that the connectors, if you look at the back, connector plate down at the bottom, so it's right down here. You can see all the various connectors. Go ahead and zoom in on that. So you can see that there's audio connectors and USB connectors, a wide variety of different connectors. So this is going to be a really robust machine when it's done. Takes actually about what, couple hours to put one of these together, and you'll save yourself $500 to $1,000. So it's a skill worth learning, because if you've had one of these apart, put it together, then when it comes to troubleshooting it later on down the road, you start hearing noise, it's a fan bearing, or you can't boot and you discover there's some wires that have come disconnected. You know these are all labeled, so you can go in there, find the right wire, and plug it back in. Not a lot to go wrong, but again, you can save yourself a repair bill if you know something about how to work in computers. I've been doing it for a while. Okay,